Hey everyone, and welcome to my YouTube channel, World of Electronics. So let's start with the question. Have you ever wondered how incredibly complex processors inside our phones and cars are created? How do engineers manage to design and place billions of components and which are smaller than virus are perfectly every time? The answer is the fascinating process called as VLSI Design Flow. And today we are going to break down using a method you won't forget. In the olden days of electronics, we could build simple circuits by hands on a breadboard like this. But today, we are dealing with chips that have billions of components and which are smaller than the size of virus. And every single part has perfectly synchronized with them. Manually building that kind of circuits are impossible. That's why the entire industry relies on powerful software EDA tools, or known as electronic design automation tools, to do this heavy lifting. But even with these powerful softwares, you just can't start randomly designing the chip. The VLSI design flow provides a systematic plan, our construction blueprint to manage this immense complexity and reduce errors. A single mistake in a modern chip isn't just a bug, it's multi-million dollar catastrophe. And at the heart of this entire process is constant balancing act. Before any design start, we have to define our goals, which are known as golden rules of PPA: performance, power, and area. Performance: how fast will the chip will be? We will do this in terms of frequency. And power: how much battery will it consume? And area: how big will the chip be? A bigger chip costs more to make. You can't have everything. The entire design is about finding the right balance. The entire flow is split into two major stages. First is front-end design, which is all about what and how the architecture planning. You can see the front-end steps here at the beginning of the flow, from specification to RTL synthesis. Second stage is backend stage, which is all about where the physical construction. This includes everything from floor planning to final verification before we send it off to manufacturing. Today we are focusing on front-end design. So let's start at the very beginning. The first step is what I call the master plan, system design level. Think of it like an architect deciding the purpose of main zones of new skyscraper. Is it a residential, office space, or a rental? In chip design terms, this is where we define major components like CPU, the memory, and peripherals. And we make a critical decision: what functions will be handled by dedicated hardware and what will be controlled by the software. For these high-level planning, the industry uses powerful modeling tools like MATLAB Simulink or high-level synthesis tools like Simon's Catapult. But for a beginner, this stage starts on a whiteboard and a free tool like Draw.io, which is perfect for mapping your system's block diagrams. So, who are the people working at this stage? The job roles here are for the bigger picture thinkers, SoC architects, system level design engineers. They are the ones who make the high level decisions. To excel here, you need to master subjects like computer architecture, embedded systems, and have good understanding of operating systems to make software versus hardware decisions. Once the master plan is set, it's time for detailed blueprints. RTL design. The analogy here is to creating detailed architecture blueprints for every single floor of the building. In chip design terminology, this means engineers write code in languages like Verilog and VHDL. These codes, called as RTL code, describes the exact behavior of every single circuit and how data moves through the chip. The industry uses advanced text editors like VIM and Emascus, often integrated into massive design suites from Synopsys, Cadence, and Siemens. For the beginners, any text editor works, and you can test your code using the free simulators in Xilinx and Intel, or open source like iVerilog. The engineers who write this code are core RTL engineers or ASIC design engineers. They are the digital blueprinters. The most crucial subject to master for this role is without a doubt digital logic design. You must live and breathe in it. Of course, you have to expertise in HDLs like Verilog, or VHDL. A solid grasp of computer architecture and increasingly scripting skills in Python or TCL at automate parts of your work. Now for arguing with the most important and time-consuming step, the full system test, functional verification. Before a skyscraper opens, we have to test each and every elevator, every vacant, and every fire alarm. Same goes for a chip. We relentlessly simulate RTL code to find and fix bugs before we build anything. This is so crucial that it can be 70% of the entire front-end effort. In the industry, this space is dominated by the big three simulators: Synopsys VCS, Cadence Xylem, and Siemens. For the beginners, simulators include with Vivado and Intel are fantastic, and an open source tool called GTK Wave is essential for viewing the results of your tests. This is a massive field, has its own dedicated specialists, design verification or DV engineers. This job is to try and break the design to find every possible bug. This is highly sought after role. To succeed, you need to advanced digital logic skills, mastery of system verilog for its powerful verification features, and understanding of methodologies like UVM. Interestingly, a good grasp of OOPS concepts is also key here. Okay. Our blueprints are verified. It's time for the contractor's job, logic synthesis. The analogy is very simple. We are handing our final approved blueprints to specialized contractors. In chip design terminology, synthesis is a software process that translates our abstract RTL code into physical list of components. The output is crucial file called as grade level netlist. Now, this synthesis contractor needs three inputs to do its job, just like a recipe. First, RTL code. This is our recipe. It tells tools what exactly to build. Second is technology library. This is the pantry. It's a file from the chip factory that lists all approved standard cells or ingredients that we are allowed to use. Third, the constraint files. These are the rules. These files are our PPA goals, telling the tool how fast the chip needs to be and how much power it is allowed to consume. In the industry, the undisputed kings of the synthesis are Synopsys Design Compiler or DC and Cadence. For beginners learning on FPGAs, which are like reconfigurable buildings, the synthesis engines inside the Xilinx, Vivado, and Intel are world class. So we can use them only. The engineers who manage this crucial handoff are called as synthesis engineers, or more broadly, CAD engineers, who manage the entire tool flow. They form bridge from the logic world to the physical world. From this, a deep understanding of static timing analysis (STA) is absolutely crucial. This is how you ensure the chip will be fast enough. This is complemented by strong skills in digital electronics and heavy scripting to automate and customize the design flow. And with that, the architectural phase is complete. We have planned our chip with system design. We have blueprinted it with RTL. We have tested with functional verification. And we have sourced our materials with synthesis. Our design is logically completed. And now it's time for the construction to begin. Next up, the backend design. This is where we get physical world of place and route. Thank you so much for watching. I hope this analogy helped you make the complex front-end design flow a little clearer. If you found this video useful, please hit and like the button and subscribe for more content. If you have any questions, please follow my blog to further answers. Thank you.